Welcome to our today's webinar about the dynamic optimization of a real-world gearbox. My name is Stefan Beermann, and together with my colleague Dr. Said Ibrahimi, I will guide you through this topic today. There will be two parts. The first part will be done by me. It will be a bit theoretical, but please bear with me. Dr. Ibrahimi will then show you the real practical application afterwards, and I promise to make it as fast as possible with a theoretical part. So the first part will consist of a short introduction, then the main structure of the method we apply, some formulas to see the theory behind it, and then we will go on to the second part. So what is the force response calculation in KISSsoft? The scope is that we have a fast analysis of dynamic behavior. We don't have all possible means to model things, so it's more a sensitivity analysis where you can find out what are the critical speeds and frequencies. Then you can also use this, of course, to optimize the design, change profile modifications or bearing arrangements. And also you will generate output for further vibration analysis in other software. For an extensive time domain simulation, use dedicated software. For this, our force response calculation is simply not intended. The main features of the force response calculation is we have a calculation of the response of a gearbox on periodic internal and external excitations. There is a coupled model of gears, shafts, and bearings, so everything is treated together. We only calculate a steady state, so we only get periodic solutions. The analysis itself is linear. Of course, stiffness and these things are non-linear, but the analysis itself is based on a linear equation system. The boundary conditions are fixed, and we calculate only in frequency domain. With this, we are much faster. The results then are given in frequency domain, time domain, and also for a certain set of speeds. This force response calculation is integrated into the system module. Here is a very simple sketch of the layout of the method. We start on the left side with a shaft model that is a beam model. Here we have a partial differential equation. Then we apply a separation approach. I'll come to that in a few seconds. With the separation approach, we can break the partial differential equation down into ordinary differential equations per shaft and per gear stage. Then from the ordinary differential equation from the shaft, we calculate influence numbers, applying a Fourier approach. The Fourier approach for the gear stage gives us a Fourier matrix using these influence numbers coming from the shaft. Altogether then is used to calculate the Fourier sum of the response to the excitations. Now, as promised, it gets a little bit theoretical. Up here you see the partial differential equation for an Euler-Bernoulli beam. Here this first element is sort of the stiffness of that beam. We have also the time derivative of that stiffness in here with some damping factor in front. So this is a damping element we have built in. And then here the last element in the equation is the excitation times sort of the mass. This is the mass times the section, cross section. So this is the influence of the acceleration of one cross section. Now we apply this separation approach. It simply means that for the solution z of x, t, with these two variables x and t, we make an approach of two functions a of x only in space domain and b of t only in time domain. These functions are further broken down into individual components an of x dependent on n omega being a frequency, omega a base frequency, n omega a specific harmonic. And the same for b, we have here a component bn of t, also dependent on n omega. A requirement is that all these ans and bns are linear independent of each other, so that we can sort of take the sum apart. For bn of t, we will later get time Fourier sum beta n, beta being a Fourier coefficient, times e to the power of in omega t, I being the imaginary unit. Since a and b n are linear independent, we can take the sum apart. I dropped the index n here, so this equation is valid for a specific n, as you can see here as a parameter for a. So we can break down our partial differential equation into this equation where we put in the separation approach and sort for a and b. Now we can sort everything with a to the left side, everything with b to the right side. That gives us this fraction here with the components of a equals to minus this fraction with all the components for b. Since on the left side we have only x, on the right side we have only t, both of these fractions need to be constant with some constant. Since we want to have only steady state, which means periodic solutions, we can further derive that this constant needs to be this value here, only dependent on the base frequency omega, the current order of the harmonic n, and our damping factor. If we put that into the partial differential equation that we just derived, we can then get an ordinary differential equation for the space and also for the time component. So what did we do? In a simplified way, we look now at one gear stage here with these two shafts, two gears, and a spring between the two gears that is the meshing, the teeth of the gears replaced by a spring. So what we did now, we looked at this force that is applied from the spring to each shaft. This is our gear meshing force. We took the gears out. So we have now an ordinary differential equation left for the shaft and the second one for the gear stage. And the common mutual component in both is this gear meshing force Fz of t that can be represented with some Fourier sum. The last detail about this meshing force here. The meshing force is calculated by multiplying the displacement of the gears as z of t times the stiffness of this spring in the meshing, or the spring that replaces the teeth. If we replace both of these time functions with the respective Fourier sums, we have first of all this stiffness function here in the background. This is calculated using our contact analysis. And we also have a representation of the displacement of the gears using a Fourier sum. If we apply these two sums, we can do this using the fact that if we multiply two exponential functions, we simply add the exponent in this function. So we have now under this double sum, this delta n times gamma k, the two Fourier coefficients, and we have the function e to the power of I n plus k omega t. So what in the end we accomplished is we had two sums running from minus n to n and minus k to k. And now we have a new sum that is running from minus n plus k to n plus k. So we added additional frequencies that consist of the combinations here in this exponent of the individual frequencies we've put into that product. And with this last slide from me, I will hand over to my esteemed colleague, Dr. Ibrahimi, who will guide you through the more practical application of this theory.
Thank you very much. So good morning or good evening, good afternoon, everybody, depending on the country that you joined the webinar. Before I start my main session, I would like just to give you a short introduction to the discrete Fourier transform formulation that we use. So as it was already demonstrated, you realize that the formulation of the force response analysis is based on the frequency response approach. In the force response analysis, basically we deal with the excitation and responses represented as harmonic functions, and these functions simply contain harmonic terms with excitation frequencies and corresponding amplitudes and phase angles. As you know, also in the real applications, mainly the gearboxes are subjected to harmonic or transient excitations, and the resulting responses, for example, displacement, velocity, or acceleration are measured, and the relationship between the input and the output signal is typically expressed in the frequency domain as a frequency response function. In this context, the discrete Fourier transform is used to convert the time domain signals into the frequency domain. So if you look at the figure represented in time domain, this is a typical excitation force. And based on this approach here, we represent this function as a summation of some periodic function dependent on number of harmonics, which is required. Then when we transfer this function from time domain to frequency domain, we deal with the figure represented, demonstrated on the right. And here simply we deal with some frequencies, and corresponding to each frequency, we have amplitudes and phase angles. So if you look at this formulation, it's quite simple representation from time domain to frequency domain. There are several key benefits of this approach, as my colleague Dr. Biermann just mentioned. One of the most important benefits is that we can have a direct insight to the system dynamics through this approach, and it simplifies the system in a linear system of equations. Therefore, it's quite practical and easy to identify the resonances and critical speeds. And it facilitates also the model validation and updating. As I show you also in this presentation, you see these points exactly, and therefore we can also consider the point that this approach is very, very efficient, especially for a steady state approach, and it enables us to optimize the gearbox. Now, before I start my main topic, I would like to give you a short overview of some topics that I will present. So I will present the introduction and motivation of this study. Then I will focus on the analysis steps in KISSsoft. Very shortly and briefly, I will introduce the force response module. These three topics are the preliminary steps. Then I will describe the model, which is considered in this study. In KISSsoft, before doing the force response, we have to do the contact analysis result, and based on the contact results, we have to get the excitations. And then based on the shaft calculations, also we can identify some shaft geometries. Altogether, we use this information to the force response analysis, and finally, after calculation of the results through the KISSsoft Recordine interface, we export the data for Recordine for NVH analysis. So this step can be generalized to any other software which loads either time domain or frequency domain input data. Then I will follow also the analysis steps in Recordine to shortly explain how we can integrate KISSsoft with Recordine to do the NVH analysis. And finally, I will focus on the experimental results, and I compare the experimental and simulation results, and I will finally conclude my presentation. At the end of this webinar, you see also some slides. I will not explain them, but for your information, if you would like to know how to use KISSsoft, the Recordine based on the KISSsoft results, just read the last part. So the case study presented here focuses on a 4-gear gearbox consisting of a chain of 3 gears and operating at identical meshing frequencies. At top left, a 2D schematic view of the gearbox is shown here. And this image illustrates the general layout and several mounted components. In the center, the 3D system module is displayed, which is built in KISSsoft system module, and it includes the housing and internal drivetrain components. The input and output couplings are also highlighted for clarity. At the bottom right, the experimental setup here is shown, which fully assembled gearbox and used for dynamic testing and validation. Overall, the gearbox represents a typical speed reducing system with a transmission ratio of approximately 3, and this makes it a well-suited system for analyzing vibration and noise behavior under realistic operating conditions. So what was the problem that we focus on this case study? The model was initially produced too much noise, even after applying some tooth modifications, and therefore, based on the collaboration that we had with the customer, they tried to do another optimization level, and the original design employs some cylindrical roller bearings with internal clearance. The bearings are defined as ISO 5753, and all variants assume 0 clearance. Now, in this optimization process, they try to optimize the case study based on the adopting different configuration for bearings of the intermediate shafts. So they consider 4 different variants starting from V1 to V4. And finally, they realized that the results, the simulation results and experimental results based on the last variant V4 was the best case study, and therefore they confirmed the model's superior performance in reducing the noise. In KISSsoft, first we have to do some static analysis, and then we go to the dynamic analysis. So the steps is, as you see here, the model is built in the system module. Then we do the shaft calculations. This step is necessary to get some geometrical information and also the bearing stiffness values. Then we do the contact analysis. This is very important because the results of contact analysis are used as a source of excitation to the gear meshes, and therefore all outputs are all outputs of the force response simply depend on the settings of the contact analysis. Then in step 4, the main dynamic analysis is started. We do the force response, and the force response, there are several outputs. But the most important is to check the dynamic machine force as well the bearing reaction forces, which are important for noise analysis. Then we export the results and we generate an interface file together with time domain excitations to be used in Recordine. At the right, you see also a schematic view of KISSsoft, which contains the model in 3D view as well the 2D schematic of the sketcher. This sketcher is a newly developed feature that enables designers and engineers to easily and quickly build a model. So what's the force response and why we call it force response? Force response is simply the calculation of dynamic responses of drivetrains. Under the period excitations, we consider different source of excitations. This sketcher, this image that you see here illustrates the data flow for the force response calculation in a gearbox system. This is very general. I didn't explain details here, but the analysis takes an input, the results from shaft calculation, contact analysis, and prepare some data. This step is done only once before the main force response analysis. And finally, on the right, you see that the outputs include the vibration behavior of gear meshes. It can include gear mesh forces, dynamic transmission, aerodynamic meshing stiffness. Then we have bearing reaction forces, bearing moments, and some other outputs. For outputs regarding shaft, we can consider some documentation points and calculate displacement, velocity, acceleration, or some other values, for example, like forces and moments at a certain section of shaft. And finally, we can visualize the system in 3D to better see the effect of excitation on different components. In the force response, based on my previous slide, we can distinguish between 3 different steps. The pre-processing step is the first one. I go fast through this slide because it's already mentioned somehow in the previous slide. So we do the shaft calculation, then we go to the contact analysis. In the contact analysis, the most important outputs are the transmission error and nonlinear stiffness that they are used for calculating excitation forces. So based on the results from shaft calculation and contact analysis, then the system data are collected and they are used in the force response module. This step is performed only once. So if you change any setting which is not directly related to the shaft or contact analysis, force response will not use again this step just to save time and just to speed up the calculation process. Then in the main step, we calculate the system equations. Based on the approach that my colleague just mentioned, a couple of dynamic equations are generated in a matrix form. They include the excitation frequencies from all sources of excitation, and then they are solved in different approaches. I will explain this later. And then finally, the dynamic meshing forces in frequency domain are calculated as the output of this step. So in the main step here, since the excitations come from the meshing stiffness, the goal is to calculate the meshing stiffness in the meshing contact forces in frequency domain. Then in the last step, in a post-processing step, we use the results from main step, and we calculate other outputs regarding bearing, shafts, and 3D deformation. But the process is as follows. First, we calculate everything in frequency domain. That's why if you use force response, you realize it's fast enough to calculate for speed range and for including many harmonics. But depending on the data that you assign for time domain setting, we transfer the data from frequency domain to time domain. And finally, the results in the speed domain are calculated from time domain. So the output finally can be used for NVH purposes and acoustic simulation in another software. So the key features of the force response is that we can set the gear mesh parameters, the stiffness models, and transmission error. It's possible to include multiple harmonic excitation as well as single harmonic excitation. We can, when dealing with several pairs, we can exclude or include individual gear pairs as source of excitation. This feature is a nice feature which gives more insight into the effect of each gear pair separately. And the outputs are calculated in frequency, time, and speed domain. Depending on the usage that we follow, we can get benefit of all these output types. And we can also include the excitation from gear meshes, from unbalanced mass, and recently from torque ripple, which is very, very important, especially when dealing with electrical vehicle. For calculation of the shaft dynamic, the shafts are considered as flexible bodies, and we can include the results from either Euler-Bernoulli or Timoshenko beam theories. So you see that on the right side, the main window for setting parameters regarding meshing stiffness, excitation, force type. For dynamic modeling approach, we can include bending and torsion, or only focus on torsion responses. Regarding the solution approach, we can solve the equations either from direct approach or alternatively, we can use the iterative approach. So then the key benefits that we can consider from the force response, based on the formulation that we use, we can quickly and easily detect the excitation orders and frequencies. This is very important, especially in diagnosing systems, and the calculations is done iteratively for all running speeds. For the torque ripple excitation, we can include either time input parameters or frequency. Here you see a typical torque input in frequency that we use in force response. And the effect of microgeometry optimization of the gears can be used to predict the resonance behavior of the prototype before building the model. So on the right, you see the Campbell diagram of a gearbox. Then here you see, for example, the dynamic forces amplitude calculated at different speeds. Here you see the dynamic factor, which is simply a magnification factor that shows the effect of excitation on the system response at gear pairs. And here you see a 3D visualization of the movement of different bodies. Now in this industrial gearbox, you see that it contains 4 gears, 10 bearings. We consider the input torque 400 Newton-meter, and output torque is calculated. So these are the typical values that are used for building the model in system module, and based on this, it's also used for construction of the real model. Here you see on the right side the sketcher view of the model. So it shows the power flow direction from the input coupling to the output coupling. Regarding the mesh properties, I also bring here some general information regarding the teeth number, phase width, profile shift, safety factors, and gear profile. These are typical values that are used for this model, and some micro geometry modifications are also designed and applied, but they are not mentioned here. After building the model, we do the contact analysis. In KISSsoft, the contact analysis is based on the well-known Weber-Benashek approach and use in analytical formulations for quasi-static analysis. So On the right side, you see that the transmission error, stiffness, and force excitation forces in both time domain and frequency domain are shown. And according to the results, especially when focusing on the results in frequency domain, you realize that only first few harmonics of the excitation force are dominant. It's very, very important in the frequency force response analysis before selecting the number of excitation harmonics to have a look at these results and to distinguish between the effect of different harmonics and to select the proper harmonic number. In this example, we can consider 1 or 2 harmonics, and we can, based on the first or the second harmonic, we can make sure that most important excitations are considered. Now the goal is to, as I mentioned before, the goal of this optimization is to deal with the original design, which has noise, and then we try to modify the model only by changing the bearing configuration. So all other parameters are kept constant except the bearing configuration of the intermediate shaft. As you see here, for example, the original model contains the cylindrical roller bearings of type of SKF, and the axial offset is 0. On the other hand, when we consider other configuration, variant 1 and variant 2 from the table is clear that we consider taper roller bearing setup. The difference between variant 1 and variant 2 is that for variant 1 there is no axial offset considered, but for variant 2 we have axial offset. Then we deal with variant 3 and 4. They have also taper roller bearing, but instead of X setup we consider O setup, and the axial offset again we have 0 or a defined value for axial offset. So the distinction between all variants are simply coming from bearings and the amount of axial offset which is considered. Just to show you how the bearing selection can change the results, I quickly explain here some results from shaft calculation. You see here for shaft 2 and shaft 3 that are intermediate shafts. The deflection along the shaft index and the components are shown, and then we have also the maximum deflection. And here below I also showed the bearing reaction forces. So when we compare the results of deflection and bearing force for all these different variants and compare with the original result design, we realize some important features. But after that, when we conduct a dynamic analysis, you see that we cannot make a one-by-one relationship between the static calculation and dynamic calculation. So it's very important to follow this when we approach the dynamic results. Now, for example, for design V1, compared to the original design, we see here we have even higher deflections. So the deflections are higher. And for the bearings, for bearing 4 and 6, the bearing reaction force are even increased, but for bearing 7 and 5 and 7, they are decreased. Now, when we go, so this is without offset, the X setup without offset. Now, when we approach to V2 design, we see that the deflections are, the maximum deflections are decreased significantly compared to the previous design. And for the bearing, we see also some differences. So when we compare design V1 and V2, the difference is only the axial offset. And we realize that how the stiffness is changed based on definition of axial offset, and we see directly the effect of a stiffness variation of bearings at for different outputs. Then I conduct also the shaft calculation for design V3. Here we see the very low max deflection, and regarding the bearing forces, we see some differences. And finally, when we go to design V4, we see compared to V3, the deflections are even high. even we added the axle offset, and the effect of this setup, since here we deal with O setup and the direction of the force on the bearing racing is changed compared to the other design variants. So we see also this difference. Here in this slide, I just summarized the results. I will not go through this. I skipped this part just to go to the dynamics. So here on the left, I just summarized the results from bearing forces, and on the right, I summarized the results from the maximum deflection. This table summarizes all important results which are calculated based on design configuration. Now we proceed to the force response. First, we consider number of speed, 300 speeds. The speed ranges from 1,200 to 3,000 revolution per minute. I checked the effect of different harmonics. So here, if I calculate the dynamic factor based on the first harmonic, we see a very high peak. This is not realistic in general, because here I neglect the bearing damping and just to better check the effect of bearing configuration. But in reality, we know that the bearings have some kind of damping and energy loss issues, and therefore in reality we deal with much lower dynamic factor. Now when I consider instead of one harmonic, I include also the effect of second harmonic and then third harmonic, we don't recognize much different, especially at critical speeds. Just some differences can be seen, especially at lower speeds, but I think for this example, it's enough to consider only the first or the first harmonic or the first two harmonics. Now, when we compare the dynamic factor for all variants, we see a significant reduction from V1 to V4. I plotted the dynamic factor in the same scale, so you see the dynamic factor is scaled on all in figures the same. But when you look at the results, especially at critical speeds, you recognize that we see significant decrease in the dynamic factor. Since the dynamic factor characterizes the machine dynamic force, we can expect that the design variant V3 or V4 would give less noise when we compare to other to the optimal design or other variants, for example, V1 or V2. Then after calculating the critical speeds, I just considered the 3D visualization of the results. And here again, based on the visualization of the movement of different elements, we recognize that the model built based on variant V1 has a very high oscillation. They are shown in a very high scaling factor just to magnify the movement. But for example, when I consider the movement of different variants, we see that, for example, especially for the last gear, variant V4 shows lower vibration. Here I'll also summarize the peak-to-peak bearing forces at critical speeds. And just to summarize, we see that for each bearing, I showed the highest peak-to-peak force in red and the lowest in green. And when you compare, variant V1 even is exposed to higher bearing forces even compared to the original design. But when we approach to V2 or V3, they are a little bit moderated. And finally, when we focus on design variant V4, we see significant reduction in peak-to-peak bearing force. It's very important to, before doing the NVH analysis, to check the peak-to-peak bearing forces, because they consider the source of excitation to the housing. And then I consider the Campbell diagram, again, based on the first, second, and third harmonics. This, again, is a validation that for this test case, it's enough to consider the first few harmonics. So when you look at the Campbell diagram in 2D or 3D, You see that the lines are evenly spaced in frequency. So I know that all of you are already familiar with this type of data. And here, based on this Campbell diagram, we can also expect that the first harmonics, as you see here, at critical speed results in a very high noise in general. But for the other harmonics, we can neglect simply the effect of these harmonics. Now, in the last step of KISSsoft recording interface, we, based on this module, we set some parameters for the housing built in Recordine, and also we can select bearings. We can include all bearings or some bearings from the list and export all bearing reaction force in time domain. This is the last step down in KISSsoft, and then we proceed next to Recordine. So for Recordine, we have to follow other steps. First, we have to load the model and excitations from KISSsoft. And then we have to do the modal analysis of the housing to recognize the eigenmodes and eigenfrequencies. And then we perform the dynamic analysis as the application of bearing forces calculated in KISSsoft. And finally, we do the acoustic analysis. So it can be considered as ERP calculation or sound pressure analysis. So now we come to the most important part for the experimental results. We received some results from our customer, but here I show only one certain part because this can be done for other points. Here on the left side, you see that the sensor position is marked, and on the 2D view, the sensor position was placed here. I show in my mouse, and then the goal is that when we build this model based on variant V4, so in the experimental setup, the goal is was to measure the velocity at different points, because the velocity, the fluctuation of velocity, can be a measure of noise. Here I showed some experimental result. So the numbers on the figures are not shown, and this is due to the policy between us and our customer. Just I briefly give you some general results here. So on the left, you see variant 3, and on the right, you see the results of variant 4. For variant 3, they recognize that the highest peak for velocity at that sensor position was detected as this speed, and the amplitude was about 2.6 millimeter per second, and the corresponding frequency was 1170 hertz. On the other hand, for variant 4, they also considered another axial offset. So the axial offset here is different than before, because we did different simulations, but here just I consider one case study. And you see by comparing the peak values, the reduction is about 30% of the velocity measured by sensor. So now I used the KISSsoft results to check the dynamic machine forces, and here you see on the left the force amplitudes for variant 3, and on the right you see for variant 4. And again, you see that only the first two harmonics are dominant, and we simply neglect the other harmonics. The change percentage from variant 3 to variant 4 based on the first and the second harmonics are reported here. And you see, for example, for the first pair, comparing the first harmonic, we see a significant decrease, but on the other hand, for the second harmonic, we see a little bit, it's about 26% increase. But for other pairs, the second pair and the third pair, for two harmonics, we see a reduction in the peak-to-peak forces. So now if I continue to do the analysis of acoustic calculation based on ERP, equivalent radiated power, which is a measure of noise emitted from the housing surface in Recordine, I show the final results based on the KISSsoft calculation. So the color distribution shown on the housing is simply a representation of the noise from the housing. Blue regions indicate areas which emit less noise, and red regions are exposed to higher noise. As you see here in the formulation of the ERP, the velocities are also involved. Therefore, it's very important also to focus on the sensor output for velocities. Here I show you the two images. On the left, you see the ERP for variant V3. The maximum ERP detected was about 7 watt, and here on the right, you see the same a parameter, but calculated for variant V4, and the maximum was about 5.8 watt. So here we already see a reduction of the ERP from variant V3 to V4. But to better visualize, I show here in a video that please have a look more on this region, and you see that this region I show with my mouse shows a significant decrease when compared in variant V4. So there are two benefits from this video. First, we can distinguish between the ERP visualization for two models, and then we can also see which regions of the housing emits higher noises. And finally, when I look at the calculation results in Recordine for the velocity sensor, so here in this image you see two plots. The orange is shown for variant V3, and the blue is shown for variant V4. I skipped the first part in time domain because the first part was just transient data, and I focus on the second part, which is the steady state results. And then if you look at the peak-to-peak velocities for both variants, for example, for variant 3, we realize the peak-to-peak is about 5.5 millimeter per second. And for variant 4, the peak-to-peak is about 3.72. So the amplitudes are simply we have to divide these values by 2 to calculate the amplitudes. And here it shows the reduction is about 32%, so which has a good agreement with the experimental result. Another important fact which can be seen from this figure is the frequency. If we consider, for example, a point which the peak values are over each other, and then we count, for example, the number of oscillations, and then divide over the time, we can simply calculate the frequencies. And here we realize that the results catch exactly the frequencies reported in the experiment. So based on this simple result, we can identify the amplitudes as well as the frequencies. I would like to conclude my talk. So the KISSsoft study presented here was a real 4-gearbox system, which was originally which produced much noise at the beginning. Then we consider 4 different variants from V1 to V4 just by changing the bearing configuration. And from the dynamic calculation, we realized that variant V4 exhibit the lowest overall dynamic forces and the most effectively suppressed resonances compared to the original design. The values are used for building another model, including the housing and the gear train in Recordine. And finally, the simulation results computed using KISSsoft were compared, and measured data from the test rig showed the good agreement. The most important point that I want to highlight is that the Recordine here was used to evaluate improvement in the housing. When acoustic analysis is not the focus, we can consider the peak-to-peak contact meshing forces and bearing forces directly in KISSsoft. And based on only these results, we can characterize the level of improvement even without considering the results in Recordline. So it's very important to consider this. With this slide, I concluded my talk. Just for your information, if you proceed to the next slides, you recognize all the steps that are used for building the model in Recordline. So please have a look. And if you have any question, you can contact me. I don't go to the detail of this part, just I skip this part. I would like to thank all of you for being here and attending the webinar. And if there is any question, I would like to answer.
Okay, thank you, Dr. Ebrahimi, for that interesting talk. We have actually currently one question already in. If you want to ask any questions, please use the question answer part of this presentation software and send the questions. We have some minutes left for answers. So the first question is, how did you decide which modifications to apply in V4 in order to get the optimum solution?
So thank you for your question. As I mentioned at the beginning, we didn't decide ourselves to change bearing configuration from V1 to V4. This was selected before by our customer and applied directly in KISSsoft. Just in order to repeat the process, I used their data, but based on the meshing forces calculated from each bearing based on the stiffness values, we can build a process how to change the bearing configuration in order to somehow stiffen the model for having better NVH prospect. This is all what I can mention because I don't have details about the bearing selection process that the customer did.
Okay, thank you. There's currently no other question coming in. If you have some questions after this presentation, you can always send them to us by email to the email address in the presentation here on the last slide, and we will answer it by written answer afterwards. So thank you everyone for attending, and thanks again to Dr. Ebrahimi for this presentation, and I wish you all a good rest of the day.
Thank you and bye.